Well, chapter 19, electric potential and electric field. Just as we begin, I want to tell you the big difference is that electric potential is a scalar, while electric field is a vector. So, potential being a scalar, it's easy to work with it. You do not have to resolve it into its components. You can just add or subtract because they are just numbers. Now here what you see is an electric field, and of course you have two plates, one positive, the other negative, and the electric field goes from the positive to the negative. So if you take a positive charge or simply let it free here, it's going to go on its own to the negative plate. And that's just like if you have an object at the top of a hill, it's going to roll down by itself. Now here we know that its potential energy is changing into kinetic energy. Or that is gravitational potential energy changing into kinetic energy. Now the difference here is that the electrical potential energy is changing into kinetic energy. Same concept, as you can see, the change in potential energy, electric, is equal to kinetic, change in kinetic energy. And what a battery does is simply, it drives the charges through the conductor here. You can see the charges moving, negative charges going into that light bulb, into the filament, back again. And so the battery is using its potential in order to drive the charges. So the battery is doing work, and it always goes from a higher potential to a lower potential. Positive charges, go back and check this. A positive charge by itself goes from a higher potential to a lower potential. Okay, that's what you see here. Now, since the electric potential energy is changing into kinetic energy, you have this equation. Now, of course, that's kinetic energy, that is the charge, and that is the potential difference. So if you know the potential, as in this case, 5,000, you put it here. And if you know the charge and the mass of the particle, you can calculate its velocity. That must be clear enough. And if you have two plates set up like this, the potential difference between the plates A and B is defined as the work done to take a 1 coulomb charge from one plate to the other. So you have this very important formula. Potential difference between A and B is work over charge, and that gives us the unit joule per coulomb, which is also called a volt. And again, remember that the electric field is the potential difference divided by the distance. It's a vector, while potential is a scalar. And the unit is volt per meter. So if you have the plates closer together, then the field is going to be much bigger. Okay? That's a Van de Graaff generator working using the principle of electrostatic charging. One important thing here is that because it's connected to the ground, and the potential of the ground is taken to be 0. So that is the important point here. Whenever you connect anything to the ground, the potential of that part is 0. So there is a potential difference between the sphere and the ground. And since you take the potential of the ground as 0, whatever is the potential of the sphere is going to be the potential difference, because this term is 0. And again, the Van de Graaff generator picks up charges because of electrostatic induction. All right, and I'm not explaining how it works here, but that's the deal. Now here you have equipotential surfaces, and Equipotential surfaces or equipotential lines are those surfaces that have the same potential throughout. So here the potential throughout this sphere, see, although you see it as a circle, it is three-dimensional. If you have a point charge, all the equipotential surfaces are going to be spheres. And to move a charge from one point to another point on an equipotential surface, you do not have to do work. That's point number one. Point number two, the electric lines or the electric intensity is always at right angles to the equipotential surface. Look at this angle, it's 90 degrees at any point, and that's always true. And of course, work is required to move the charge from one equipotential surface to the other. Okay? So to go from one to the other, yes, you have to do work. But to go from one point to another on the same equipotential surface, you don't have to do work. Well, this just shows how the electric field lines and equipotential lines are for two equal but opposite charges. Remember that the equipotential lines are always perpendicular to the electric field lines. And the potential is positive near a positive charge and negative near a negative charge. Therefore, if you go in this direction, you are going from a higher potential to a lower potential. When you're moving in the direction of the field, look at that. That's the direction of the field. When you're moving in the direction of the field, you're always going from a higher potential to a lower potential. Again, this is how the equipotential lines will look and how the field will look like if you have two charges close to each other. And here you have two plates again. Actually, the potential of the negative plate is negative and that of the positive plate is positive. So it should be like plus 50 and minus 50, but what we can do to make stuff easy is to take the potential of the negative plate to be 0 and take the potential of the positive plate to be 100, because then the potential difference is 100 volts, which would have been the same if you had taken it as minus 50 and plus 50, right? So the negative plate or anything connected to the ground or connected to the negative is always assumed to be at 0 volt. And that's what it means here. And one more time, I just wanted you to notice that the electric lines are perpendicular to the equipotential lines. Look at that. These are the equipotential lines and they are at right angles. And this is a capacitor. A capacitor is an arrangement used to store charges. And capacitance is capacitance is defined as the ratio of the charge to the potential or to the voltage. That gives us the unit. It is going to be coulomb per volt, which is called farad. And one plate will have a positive charge. If whatever is connected to the positive terminal of the battery, like this is the positive, that's going to get positively charged, and the one that's connected to the negative is going to get negatively charged. And if you disconnect the battery now, the charges will remain here so long as you have an insulating substance separating the two plates. As you can see down here, you have an insulator between the two metal foils, aluminum foils normally, and then you roll it up to save space. That is what a parallel plate capacitor is. And the capacitance is actually given by Ka epsilon naught by D. K is not 9 times 10 to the 9, but it's called the dielectric constant. It depends on the material used. And the higher the dielectric constant, the bigger the capacitance. And also A is the area of one of the plates. Epsilon naught is called the permittivity of free space, it has a value 8.85 times 10 to the negative 12. D is the distance between the plates. Therefore, if you decrease the distance between the plates, capacitance increases. Well, I've written the formula one more time. And if you're asked to calculate the area, you can rearrange this and just trying to find the area of the plates required to have a capacitance of 1 farad. So you have 1 here, and we assume that the distance between the plates is 1 millimeter, which is 10 to the negative 3 meter. K is assumed to be 6 for the material used, and this is epsilon naught. When you calculate this, you get a huge number showing that capacitance of 1 farad is really big. Now in this one, you see what happens to the insulating material kept between the plates. You see that it gets polarized. It separates, its negative and positive separates, but all through the inside they cancel out. Like this positive cancels this negative, and this negative cancels this positive. But you see at the end phases, you have no cancellation, so you have positive here and you have negative here, and these charges actually hold the charges on the metal right in place so they do not leak away. So that's the advantage of using an insulator between the plates. And in fact, because the field is from positive to negative, you can see that inside this insulator you have a field that is opposite to the field that was originally on the plates. So as a result, you see this as a result, the dielectric or the insulator reduces the electric field strength. It reduces the electric field strength, and now the voltage is smaller. That means it has a larger capacitance. You need to get the connection. Let me highlight that. You need to get the connection between electric field is lower. That means the voltage is also smaller, but the capacitance becomes larger. That's the idea of using a dielectric. And when you look at this, all right, I'm not going to talk about that, but here you have 3 capacitors connected in series with each other. And this is like, if you compare these 2 diagrams, you see that this is like increasing the distance between the 2 plates, right? Look at this. And therefore the total capacitance decreases, and it's given by the sum of the reciprocals. So 1 by Cs, that's the total capacitance when you connect it in series, is given by this formula. But if you connect them in parallel, that is like increasing the area of the plates. So that's like increasing the area of the plates, and therefore the capacitance increases. And in this case, to find the total capacitance, you just have to add the individual capacitances. So that is basically this chapter. And this is just an example of how to calculate the total capacitance. These two are in series with each other. So you got to find what they are, and then that combination, that series combination, is in parallel with the third one. So we'll work out problems in class, but these are the basic concepts that you need to know in this chapter. All right, and here you see in a calculator, the memory is actually the energy stored in a large capacitor. Okay, so that is how a calculator stores the numbers. And here you have defibrillator, and defibrillators are really important to save lives. And I hope you will read a little bit more on this and see how a capacitance is used in this. Okay, in a semi-permeable membrane, because of the difference in ions, you have a potential difference between the two sides. As you can see, all the positive ions have lined up here. You have the negative here, so that creates a potential difference. So thank you and good luck.